when we color knots and when we color rational tangles, the one requirement that we have for what makes a coloration valid and this is true for both knots and tangles, is that at every crossing, everywhere that we have a crossing of strands, what has to be true about the colors of the strands that are incident in that crossing? So there's two possibilities. One of them are either all different or all the same, right? Or all the same. And we can mix and match, right? Some of the crossings might have all different colors and some others might have all same colors. But every crossing needs to meet one of those two criteria, right, in order for the coloration to be valid. What I found in thinking about this a little bit more is that an equivalent way of saying this that may be a little bit more useful is to say that if two colors are the same at a crossing, then the third also has to be the same. So as soon as I choose two equal colors at a crossing, that forces me to have the third color be the same as the first two. And then if I replace the word equal here with different, so if I choose two different colors at a crossing, then that forces me to have the third one be different from the first two. Right? That's another way to think about what makes a coloration a valid coloration. And this is true for colorations of knots. It's also true for colorations of tangles. And one of the ways that we found to encode that requirement into arithmetic. So this was the key observation that got us started last time into thinking about tricolorations. So for tricolorations, where we represent our colors by numbers. So that's the first thing that we need to do in order to make this into an algebra problem. So maybe the color red is 0, the color green is 1, the color blue is 2, or something like that. So this is my crayon box here. Then we found out last time that tricolorability, a valid coloration, means that a certain equation is true at every crossing. What was the equation?
X plus y plus z
0 mod 3.
0 mod 3. Yeah, there we go. X plus y plus z had to be congruent to 0 mod 3. Right? In other words, add together x plus y plus z, and I have to get a multiple of 3. Right? It could be 0, it could be 3, it could be 6. As long as it's one of those three, this modular arithmetic equation is satisfied. Right? And so in my videos, I call this the magic equation for tricolorability. It's how we turn three colorations into an algebraic question. Later on, we want to find out a magic equation that works for more than 3 colors. But we're going to start by getting a lot of mileage out of this one for just 3. So that was, for knots, something we found out was not always possible to satisfy, right? That some of the knots that I handed out for you to play around with, as hard as you tried, some of them you couldn't come up with a way to tricolor it. One of our goals for today should be to figure out how to prove that just because you couldn't find a tricoloration, how can we prove that one does not in fact exist without having to check all of the possible permutations of ways to assign 3 colors to n different arcs in your diagram. And having this be an algebraic equation is going to give us a way to do that, to make that rigorous, to actually prove when a tricoloration does not exist. Or if tricolorations do exist, what we'd love to be able to do is say how many tricolorations, how many different ways are there for us to assign 3 colors to this knot that are fundamentally different and which satisfy the validity criteria on the screen. So that's where we left off last time. And it was a hard question for knots. And the reason it's hard is that if we only have 3 colors to work with, we can't always find a solution. And we sort of started talking about this last time, and I want to pick up there. today to get us started. If we think about tangles instead of knots, then it's entirely possible that, well, not just possible, it's always the case, that the four vertices of a tangle, because they're not connected with one another, right, except in the middle, right, they don't necessarily loop back in on themselves. It's that looping back in on themselves that causes trouble for knots. But for tangles, so if we just take the tangle that was on our previous slide for a second, because the vertices of this tangle don't loop back in on themselves, it turns out that it's a lot easier to assign colorations to tangles. But what it's going to permit us to do is to use more than just 3 colors. So what we're going to talk about first is how to color a tangle using not necessarily a finite list of colors, but we can color it using the integers. So before we dig into the modular arithmetic, we'll just use regular type arithmetic for integers to come up with a way to color rational tangles. And the observation that we had last time is that we can use this magic equation for colorations of knots as inspiration for how to color a tangle. And the way that that works is if I solve this equation for one of its variables, let's say I solve it for z, minus x minus y. Or actually, let me solve it for z, why not? Minus x minus y. And if I'm working mod 3, that means that negative 1 is the same thing as 2, right? Because both of them are just 2 more than a multiple of 3. Mm-hmm. So I can replace any one of these negative 1 coefficients with a 2 coefficient instead. And classically, in knot theory, the y ends up getting the 2, and the x ends up getting a negative 1. So this equation is still the same as the magic equation if we're working mod 3. But if we remove the requirement of working mod 3, then this equation over the integers gives me a recipe for taking the colors of 2 strands at a given crossing, x and y, and producing a new color for the 3rd strand at that crossing. So if you tell me what x and y are, then I can use this equation to determine a z. And another way to rearrange this equation, I'm going to add the x to the other side. And I mentioned last time that my preferred shorthand for how this equation actually tells us about colorations is if we think of the overstrand here as the y strand and x and z as the understrands. I'm choosing them that way because x and z are symmetric in this equation. If I interchange x and z, the equation doesn't change. And so my 2 understrands, I want to play that role of the interchangeable in this equation. But what it tells me, and the shorthand I love, is it says that the overstrand color is just the average of the understrands. And so as soon as you supply for me 2 numbers that color 2 of the strands at a given crossing, I can use that principle to determine the color of the 3rd. And that should be enough for us to figure out how to color any rational tangle. All we have to do is get started somewhere. So pick one crossing and give the strands at that crossing any 2 numbers that we like, and then we can get the ball rolling to determine the color numbers. So we're going to think of the numbers as colors in the integers for the whole rest of the strand. So if I do that with this one, the conventional way to get started is to just start with 0 and 1 at the top leftmost crossing of my tangle. And so here 1 is the overstrand, 0 happens to be the understrand, one of the understrands. And so 1 needs to be the average of 0 and whatever this other one is. So what does that tell me this strand over here is going to be at this crossing? 2. 1 is the average of 0 and 2. And so that strand is going to get colored 2. That means then that this next crossing here has a 1 as an under and a 2 as an over. And the 2 needs to be the average of 1 and the other one. So that makes this strand 3. And then that means I have 3 and 2 at the next crossing. So 3 is the average of 2 and the next one. So that next one ends up being 4. So that's kind of friendly. It looks like we're just sort of building up colors as we go vertically down this vertical twist here. We start with 1 on this arc, 2 on that arc, 3 on that arc, and 4 on this arc. And notably, we're going to pick up on this as a important quantity for us. If I keep track of what are the colors of the strands that end at the vertices in my tangle, the one at the upper left I labeled a 0, and now the strand that terminates in the lower left, in the southwest, I have 4. Okay? Let's keep going. You can figure out what happens on the right side. As I continue to the right side, I have this strand here that I haven't colored yet, meeting up with this strand here that I've colored a 1, and also another understrand that we don't know what the color is. So we need to know what the color of this strand right there is before we get started. And we can find that out by noticing that at this crossing, an understrand of 3 and an overstrand of 4 are meeting. And so that makes the other understrand, the number whose average with 3 is going to give me 4. So that makes this strand 5. So this strand here is 5, and that becomes now the overstrand of this crossing in the tangle. One of the understrands here is a 1. So if we take stock of where we're at here, a 1 is an under, a 5 is an over, and so the average of 1 and something is going to give me 5. 9, yeah. So now we've kind of had a jump. Somehow, maybe that jump tells us that we've now switched from looking at vertical to looking at horizontal twists, perhaps. But now I've got a color of 9 for this strand, and that means I have a 9 and a 5 meeting at this crossing, that 5 coming from over here, right? And so the average of 5 and something is going to give me 9. 13. 5 plus 13 is 18, divided by 2 is 9. Yep, right. So we've gone up. Notice, by the way, what the progression of these numbers is here on the strands that are now involved in the twist on the right. 5, 9, 13. What are they going up by?
4.
Going up by 4s. Maybe that's meaningful. Let's check and see if that pattern continues. Here at this strand, I've got a 9 as an under and a 13 as an over. And the average of 9 and something gives me 13. I think it is actually 17. 9 plus 17 is 26, divided by 2 is 13. So 17 then ends up being the color for this strand that now ends at the southeast corner. And in the northeast corner, I've got this 13. Great. So what we've just done is we've integer colored this rational tangle. Every one of the arcs in this diagram has been given an integer, and it satisfies the requirements of our colorability, because by construction, at each crossing, I have 3 different integers meeting. Right? That's the case because anytime we average 2 integers and get a third, those 3 integers are necessarily distinct. That's something you should probably check. It probably doesn't take too much convincing that the only way to get 2 numbers in a 3-number average, 3-integer average to be the same, is for them all to be the same in the first place. Otherwise, the average of 2 integers is always strictly less than 1 and strictly greater than the other. So we always have distinct. But it also raises the question of how do we know that that average is always going to be an integer? How come we don't get like 1.5 in this process? So that's something that didn't happen in our process, but it's worth asking, how do we know that it doesn't? But I'm going to leave that question because it would take us further afield than I want to go right now. Cool. So this is an integer coloration. And if we were to close up this tangle into a knot, numerator close it, then somehow we'd like for this to tell us something about the colorability of this knot. In particular, we would need to assign the same color to this strand that's ending up here as 13 as we assign to this strand, which is coming up here as 0. So if I were to form the numerator closure, I would need to do so in some number system in which 0 and 13 are the same. And likewise, 4 and 17 would need to be the same. right? Because those are the strands that we're joining up if we form the numerator closure. So that's what imposes the modular arithmetic on colorations of knots. We can color tangles using integers however we like to, and we can always make that work. But as soon as we want to close up the strands back in on themselves, that's going to introduce new conditions on the numbers that we use, because we need 0 and 13 to be the same, we need 4 and 17 to be the same. And in fact, the only, let's see, there's certainly one way to make that happen, and that is to work with the integers mod 13. Right? 13 is congruent to 0, and 17 is congruent to 4. But since 13 is prime, I think it turns out that that's the only way to get that to work out. But in principle, there might be other situations where you don't have to go all the way up that high. But if we think, for the moment, just about tangles again, so we don't worry about that modularity for a second. The one thing I want to look at is, how does this tell us something about this tangle that might relate to what we already know about how rational tangles operate. So in Kaufman and Lambropoulos' paper about classification of rational tangles, they have a whole section about classifying rational tangles through their integer colorations. So the process of assigning integers in the way that we just did to the arcs in a rational tangle diagram actually can give us an invariant for rational tangles. And the way that they do that is that they actually show that when we go through the process that we just went through, that we actually do get something which is an invariant for rational tangles, which doesn't depend on the diagram that we draw that represents that tangle, but it only depends on the tangle itself. And moreover, from it, they come up with a way of determining the tangle number. So they relate this invariant to the tangle number invariant that we already know for rational tangles. And the big surprise is that they do so in a way that shows that those two invariants are actually the same invariant. So here's the way that it works. They take, first of all, the colors, the integers that exist at the 4 vertices of the rational tangle, the ones that we just put in squares at the ends of our tangle. And they just package them together into this little matrix, this 2x2 matrix they call a color matrix. And they don't do that, interestingly enough, for the purposes of doing linear algebra with this matrix. We're going to have occasion to do linear algebra later in today's class, but it won't be with this. But then they come up with this, they sort of look at what are the properties that that matrix satisfies. What can we say about the numbers that end up at the corners of an integer coloration of a rational tangle? And they come up with a few statements. The first is that any which way we do it, no matter how we start, so we started with 0 and 1 on those two strands, but no matter how we start coloring a rational tangle, it'll always be the case that the diagonal sums agree with one another. So when they come back to our diagram that we just drew, you notice that if I add up the sum of these two corners, 0 and 17, I get the same result as if I add up the other two. 0 plus 17 is equal to 13 plus 4. So they call that the diagonal sum rule. So that's true for any rational tangle, and also for any choice of starting colors. Here we had 0 and 1. So that's the first result. And the second result, and this is the big finish here, is that if we started with a rational tangle, then we can form this fraction. This fraction is formed by subtracting the colors that we had on the top, so B minus A, so subtract northeast minus northwest, and dividing that by the difference northeast minus southeast. So if I just draw on this for a second, we're taking this difference, B minus A, and we're dividing it by that difference, B minus D. And that's going to give me a fraction, a rational number. And the argument is that that fraction is an invariant of the rational tangle. So it only depends on the tangle itself and not which diagram or which form I'm presenting that rational tangle in. And so they go through some trouble to prove that for rational tangles this really is an invariant. But what's really amazing about this theorem is that they also prove in this paper that this new invariant satisfies the summation rule, that if I add two rational tangles by joining them up horizontally, that this quantity applied to the sum is the same as the sum of these two quantities applied to the originals. Also that it commutes with the opposite reciprocal operation, which remember on tangles is just a rotation of the tangle by 90 degrees. That it also commutes with the operation of reversal, reversing all the crossings in a rational tangle. That means, therefore, that it commutes with the regular reciprocal. And all of these are exactly the same properties that characterized the continued fraction tangle number of a rational tangle. And therefore, they can prove that this invariant that they created just by subtracting across the top, subtracting across the right column, and then dividing, that invariant actually is exactly the same thing as the tangle number for a rational tangle. So talk about a bonus to this theorem. So it tells us that if we want to compute the tangle number for any rational tangle, all we have to do is come up with an integer coloration for it, and then subtract the tops to get the numerator, subtract the bottoms to get the denominator. Subtract the right sides to get the denominator. So coming back to our example, here it is again. According to their construction, the small f fraction for this tangle is the difference between these two numbers on top, 13 minus 0, divided by the difference between these two numbers here on the side, 13 minus 17, so make sure to keep that order straight. Divide it up. That's going to give me negative 13/4. But then the result of this theorem is that that's exactly the same as the tangle number that we would have gotten using the continued fraction representation of this rational tangle. And so that's something that's worth checking for this rational tangle. If we just use the ordinary continued fraction representation of this, would we have gotten negative 13/4? And according to their result, that answer is yes. So what's awesome about this is the ordinary way of computing the fraction for a rational tangle required us to put that tangle into its canonical continued fraction twist form. So we might have had to do a lot of work to figure out how to express it as a combination of right twists and bottom twists. But this way doesn't require us to worry about that at all. There's nothing here that said that we had to start with some particular representation. All we had to do was come up with a coloration, subtract one way, subtract another way, and divide. By the way, one of the reasons that the numerator closure is called the numerator closure is because those are the two vertices that when we subtract them gives us the numerator of this tangle number. And the denominator is created from the verticals instead of the horizontals. That is why they're called the numerator and denominator closure. Not just in this specific example, but it turns out there's an even higher powered invariant called the Alexander polynomial that generalizes this idea and is part of John Conway's groundbreaking 1970 paper about classifications for rational tangles. But in the way that we use it so far in this semester, this is the representation for why numerator gets called numerator and denominator gets called denominator. So the question was, is there any rhyme or reason to the fact that the difference between 0 and 4 is also the same as the difference between 13 and 17? So, and the answer to that is, of course, there is a reason for that. That's not an accident at all. And one of the ways to see that is to look at the diagonal sum rule. So the fact that 0 plus 17 is the same thing as 4 plus 13, that was the diagonal sum rule. Well, what happens if I subtract 4 from both sides and I subtract 17 from both sides? Right? I'm going to find out that 0 minus 4 is the same as 13 minus 17. Right? So that's just a consequence of the diagonal sum rule. But that does tell me that whatever modular arithmetic might be necessary to give me a coherent coloration for the denominator closure is going to work for the two left-hand vertices in the same way that it works for the two right-hand vertices. Right? The difference between these two is 4. The difference between these two is also 4. Therefore, any modulus that I choose for a coloration for this tangle in which differences of 4 are trivial, so I could choose mod 2, for example, or I could choose mod 4, but we convinced ourselves that 2 coloration is not a thing, so 4 coloration is going to have to be it. Right? that that will give me a 4 coloration for this denominator closure for this knot. That's going to work on the arc on the right as well as it works as the knot on the arc on the left. And the same thing is true if instead of subtracting 4 from both sides, I subtract 13 from both sides and I subtract 17 from both sides. 0 minus 13 is equal to 4 minus 17. That shows me that that modulus of 13 that's going to work for the top strands in the numerator closure is also going to work for the bottom strands in that same numerator closure.
When we originally looked at it, I thought to myself, oh, we could use.
So that's another thing that we can tell from the tangle number of a rational tangle. So we decided now that the tangle number of this was negative 13 over 4, right? And so what we've now convinced ourselves is that 13 colors can color the numerator closure of this tangle, right? Whereas 4 colors are sufficient to color the denominator closure. Now, of course, one of those is a knot, and the other one is a link. Right? But that's okay, right? Because coloration questions about links are equally approachable with the theory that we're building up here as coloration questions about knots. So if somebody hands you a rational tangle on the street, happens to me all the time, I don't know about you, and you can figure out what the tangle number is using any method, right? Then the numerator of that fraction is going to tell me about the colorability properties of the numerator closure of that tangle, and the denominator of that fraction is going to tell me about the coloration properties of the denominator closure of that tangle. And that's nifty. Again, that reinforces why we call the numerator and denominator what we call them in this theory. So that kind of closes the loop on that a little bit. But yeah, great observation. The diagonal sum rule is what persuades us that that does work the way we want it to. So Sam's question was, now that we have a coloration, an integer coloration for this rational tangle, what happens if we just take everything mod 3? So just reduce all of our stuff mod 3. Let's actually just go through and make each of these into their residues mod 3. So 0, 1, and 2 can remain the same, but 3 becomes 0. So let me establish my 3 colors again. So if we reduce mod 3, we're just going to be coloring in all the strands that are congruent to 0 mod 3. I'm going to color those all red. So I think that's all of them there, 0, 3, and 9, because we didn't have a 6. Everything which is congruent to 1 mod 3, I'm going to color with a green. So that's 1, and it's also 13 and 4, right? 13. And then I'm going to color everything which is congruent to 2 mod 3. I'm going to color that with a blue. So one of the things that you notice about this is that because we use the magic equation to inspire this process, all of the crossings inside of my tangle, when I reduce them mod 3, still give me valid colorations, right? Because the fact that these numbers, the fact that the average, the overstrand was the average of the 2 understrands, also implies that as soon as 2 of those strands are different mod 3, the third one is also different from the other 2 mod 3. So all the crossings inside of my tangle are okay as far as this coloration goes. And so the only consideration is the one that you raised, which is now if I close up this tangle, if I try to close up this tangle, do I get something that's valid? And there, the answer is no. Because taking the numerator closure requires me to join up this 13 and the 0. In other words, this green strand with this red strand, and now I'm sunk. So at minimum, I would need to add in a new color to color that strand. And that new color would have to be different from all 3 of the original colors. And then likewise with the 4 and the 17. If I join those up, I still need to have something which is different mod. Well, it's got to be still, it has to be different still, I think, than the ones that we had. So if I added a new color to make 0 and 13 the same, I would have to add still another new color to make 4 and 17, that would make 4 and 17 the same. So this new strand that starts at this crossing and comes around to this crossing would have to be different than all the others. So that might imply the existence of a 5 coloration for this numerator closure, right? Starting with the 3 in my original tangle and just adding 2 new ones for the top and the bottom. Somehow that's not very satisfying either, because that would seem to imply that any rational tangle would be five-colorable.
Well, you could use 4 though, couldn't you? Use the same color on the top end.
But if I use the same color for this one and this one, then those two are going to be the same.
No, I
meaning
meant
right here.
the 2 orange strips that you have.
Oh, no, that was my point. So I should really color this orange all the way back to here, right?
Oh, okay.
Because it's all one strand.
Yeah.
But then I'm going to have 2 oranges meeting right there. And I can't have that unless this is also orange, and then the whole house of cards is going to fall apart, and we're going to color everything orange. Which is, a coloration. This is not a very interesting one. So what I should have done is color this bottom strand something different still. Right? And now this top numerator closure strand is still orange. And now at least, I think, we have a valid 5 coloration for this tangle. And so a conjecture that I would make about that is if the process of integer coloration for a rational tangle always gives me once I reduce it mod 3, if it always gives me a valid 3 coloration inside the tangle box, then can I always do the same process to give me a 5 coloration for any rational knot? So that might be worth noodling around a little bit between now and our next class.